Hey there, Comp 1113. Here we are in unit number 8. We're going to start talking about matrices. Uh, this is an important topic for anybody in computing because it's a fundamental part of computer graphics. We're going to start out discussing matrices, however, in a context that you're probably more familiar with, and that's systems of linear equations. So we'll apply concepts of matrices to systems of equations first. And then after we've kind of got everyone used to the whole idea of matrix notation and matrix operations, then we can start applying this to the more practical topic for you guys, which would be graphics. So today is a basic review of linear equations, and we'll learn the Gauss-Jordan elimination method. So let's dive right in. Systems of linear equations are something that you've been solving, well, probably since your early days of algebra when you first started learning about lines. Say you have two linear equations here. I wrote them. Maybe you're more familiar seeing them in y equals mx plus b form, but we certainly can write them in this form. I have two equations here, and I'd like to find a solution that would work in both. So you learned several ways of doing this. One way was you graphed the two lines and you look to see where they intersected. In fact, why don't we do that? A quick way to graph lines, if you've ever seen this website, it's really slick. It's really fast for doing a quick graph. You just type in the equations. It's basically a graphing calculator. Our equation was 4x minus 3y equals -1. And we had a second equation, which was, let's see, it was 6x minus 4y equals 2. And I missed my equal sign. There we go. You can see the two lines here. The first line was the red line, and the second line was the blue line. And the solution to the system is where their x and y are the same. So if we just kind of search around on the graph here, we could zoom in and we would locate this spot here as where they intersect. So it's kind of a nice little program for that. We can zoom out to see better where that is. What is the solution there? It looks like it's at when x is 5 and y is 7, the two lines cross. So that's a solution to a system of two linear equations. The process, it's awkward to try to find an intersection point, especially if they don't fall, right at a nice, integers like 5, 7. So, we learned other methods for this as well that were more algebraic. You probably learned the substitution method, where you take one of the equations, solve it for one of the variables, and then you substitute that into the other equation. Hopefully that's familiar. I took equation number 1 here, and I rearranged it. I just solved it for y. So I moved the 4x over to the right side, and I divided both sides by -3, and you end up with this. Now, this is my new equation number 1. In the more typical form, you're used to seeing this as y equals mx plus b, where the slope is 4/3 and the intercept is 1/3. We can take this equation and substitute it into the y of the second equation, and then we can solve for x. So substituting in our value of y into the second equation, we get this. Now we have one equation with one unknown x, and we can solve for x. Just do a little bit of algebra. We end up getting x is equal to 5. Once you know what x is, you can substitute that back into the first equation to figure out what y is. So that was the substitution method. Hopefully that's familiar to everyone. That's a prerequisite for the course. Once you get your answer, you should check it. Make sure that you stick your answer for x and y back into the original equations to make sure that they work out. So I substituted 5 and 7 into the first equation, and it checked out. And I substituted 5 for x and 7 for y into the second equation, and it also checked out. So now we're sure that this is the answer. You learned another method for this. You probably called it the elimination method, or the method of addition, where you try to get rid of one of the variables by adding the two equations together. So we'll add our x column together, our y column together, and our constants together, and ideally we'll eliminate one of those variables. We had to do a little bit of an adjustment to make this happen. So I decided I wanted to eliminate the x variable. To do that, I'd have to multiply the first equation here by 3. So 3 times 4 gives me the 12, minus 3 times 3 gives me the 9, and 3 times minus 1 is 3. I'm going to multiply the second equation by 2, or better yet, negative 2. And that way I can just add the two equations together. I basically found the lowest common multiple of 4 and 6. Remembering that if you multiply the 6 by minus 2, you have to multiply everything in the equation by minus 2 as well. Once you have your system of equations set up like this, you can just add them. So 12x plus minus 12x is 0x. We've eliminated the x variable. And then we'll add the y's. Minus 9y plus 8y is negative y, and we'll add the constants and get minus 7. So our equation ends up being negative y equals negative 7, so y equals 7, which matches what we did in our substitution method. We could have also done elimination of the y's instead. Multiply the first equation by 4 and the second equation by negative 3, and then we could add those together, and we'd eliminate the y's and solve for x instead. What are the rules for this? You're allowed to multiply equations by constants. We've been doing that forever, and we're allowed to add two equations together to get a new equation. That's going to be the first thing we learn about matrix algebra. Is basically we're going to solve a system of equations like this, but we're going to do so with, it's basically just a shorthand notation. We'll use an augmented matrix. Basically what we do is we take the coefficients of the x, the coefficients of the y, and the constants, and we put them into a two-dimensional array. We'll have an array here that has 2 rows. I'll call it R1 for row 1, R2 for row 2, and it has 3 columns. We have a column for the coefficients of x, a column for the coefficients of y, and a column for the constants. We call it an augmented matrix when we also include the constants. It's just a matrix if we just had the x, y columns. What we want to do now is basically not have to be looking at the variables all the time. We know that the first column means variable x, and the second column means variable y, and the last column means the constants. So from this matrix notation, we can always go back to the equations with that understanding that that's how we have them set up. Our goal for this is to get our matrix written in this format, where we end up having a 1 for our coefficient of x. So in the first row, we have 1x plus 0y equals something. That tells us what x is. If we can get our matrix to look or into this format, we know that x equals this first question mark, and y then equals the other one. I probably should have used maybe a different symbol here, because these values won't be the same in most cases. Like in our example, our x turned out to be 5 and our y turned out to be 7 for this system of equations. So getting the matrix from the original matrix of the coefficients and constants into this new matrix, that process is called Gauss-Jordan elimination. It's a step-by-step process. It's a nice little algorithm. Easy to code this method. So I think what we should do is just dive right into it and see if we can figure out how to get from this matrix to this one. And we really only have a couple of rules that we're allowed. We can multiply an equation by a constant, and we can add equations together. That's what we did when we were doing the elimination method with systems of equations. And that's what we're going to do with Gauss-Jordan. We're going to use those operations to get it into this format here. So why don't we do that old school rather than just watching the animation. I'm going to turn on my cursor here. And then we'll do this example. I'll write it out. Remember our equations. We had 4x minus 3y equals -1, and 6x minus 4y equals 2. And we're going to put that into a matrix. So the first equation goes 4 minus 3 minus 1. And the second equation is 6 minus 4, 2. Our goal is to get it into a form like this, where we'll have something here and something else here. Because when it's in this form, we'll have 1x plus 0y equals something. And in the second equation, we'll have 0x plus 1y equals potentially something else. Which then, using that, we know that x equals question mark and y equals double question mark. That's our goal. And to achieve this goal, we're going to do basically the rules that we're allowed to do with linear equations. In order to achieve this pattern here, the first step, or what I'm going to recommend for the first step, is to try to turn this upper left corner. This is position row 1, column 1. And I want to turn that 4 into a 1. I can do that pretty easily. I'm going to leave the second row alone, so nothing's going to happen to the second equation. I'm going to take the first equation and make that x coefficient into a 1. And to do that, I'm just going to divide each of these values by 4. or essentially multiply every value in that equation by 1/4. I'm going to say 1/4 times row 1 and put my answer here. So I'll just write a little 1/4 up here. 1/4 times 4 gets me 1. That's why I picked 1/4, because it's the reciprocal of the value that I'm trying to turn into a 1. But I have to remember to do it times, each piece of that linear equation. So my next term here is -3/4, and then -1/4. That's step 1. The next step of the process, we're going to go after this 6. We're going to use the 1 here to help us eliminate the 6 below it and turn it into a 0. Once you get 1s into the matrix, those 1s have a name. We call them pivots. So we'll use the pivots to eliminate this 6 here. When I'm trying to make a 0, I can't just divide, that row by something. I mean, I could multiply that row by 0, but then I'd just end up with all zeros, and I wouldn't be achieving my pattern here. So I can't just go row 2 times 0. So I'm going to have to add 2 equations together to achieve that. I'm going to leave the first row alone. And my goal is to get a 0 in this spot. I'm going to use the first row and the second row to achieve that. I'm going to multiply the first row by something and then add it to the second row. What is the something I'm going to use? Well, it's going to be the opposite sign of what I'm trying to eliminate. I'm going to take -6 times row 1 and add it to row 2. And then I'm going to put my answer in this matrix here. So I'm looking at the second matrix that we've drawn, and I'm putting my answer in the third. I'm going to write myself a little note. I'm going to use -6. Basically, I'm taking -6 times row 1 and then adding it to row 2 and putting my answer in row 2. You'll see how it goes here in a second. So -6 times 1 is -6, and then -6 plus 6 achieved what I wanted to achieve, a 0 in this position. This is row 2, column 1. Next, I have to do it for the rest. I'm going to multiply my -6 times -3/4. So -6 times -3/4, and then I'm going to add it to -4. Now that, arithmetic is getting hard, so I'll just sketch it off on the side here. -6 times -3/4, and then add that to -4. And then we'll see that's what's going to go in this spot. So we get +18/4 minus 4, or I guess we could say that is maybe reduce the fraction, 9/2 minus 8/2, getting a common denominator. So we'll get a value of 1/2. That's what goes here. We're not done. We still have one more to go. We're going to take our -6 and multiply it by -4, or sorry, -1/4. And then we're going to add that to this 2 and see what we get. The result will go in this spot. So what do we get here? 6/4 plus 2, which is, 3/2 plus 4/2. So we get 7/2. That's what goes here. You could probably do that in your head. These numbers are easy enough. I just wanted to, show this to you, because when you look back at it, there isn't a lot of work to see how this matrix magically turned into this one. The next step of the process, we're halfway done, is we want to get the 1 in this position. So this 1/2 here, we'd like to turn into a 1. That's the order that you do this in a with two equations. You try to get a 1 in the upper left, get a 0 below it, then get a 1 in row 2, column 2, and then finally get the 0 above it. So how do I turn 1/2 into a 1? I just multiply it by 2. So I'm going to say 2 times row 2. I'm going to leave row 1 alone. I'll put my little note up here. I'm going to go 2 times 0 is 0. 2 times 1/2 is 1. And 2 times 7/2 is 7. Notice I didn't need to do any scratch work for that one. That one was easy enough. Oh, we're almost there. We need to turn this -3/4 into a 0. And then we'll be done. So how do we do that? I'm going to leave the second row alone because it's done. I know that 0x plus 1y equals 7. I actually know that y equals 7 at this point. We're just now going back to try to figure out what x is. To clear out this -3/4, I'm going to multiply the second row times +3/4 and then add it to row 1. So 3/4 times row 1 plus, 3/4 times row 2 plus row 1. Our answer will be here. So I'm looking at the matrix above, and I'm putting my answer in the matrix below. And let's see how it goes. 3/4, I'm going to multiply by 0 and get 0. And 0 plus 1 is 1. There's a reason we do this in the order that we're doing it in. If you do this in a different order, sometimes as you're going along, you might undo things that you'd already fixed. So by doing it in this pattern of do the upper left, then do the thing below it, then do this one, and then get a 0 here, if you do it in the process in that order, you won't be messing up anything that you've already done. If you have the 3 equation case, you get a 1 in the upper left, then you get a 0 below it and a 0 below that. Then you get a 1 in the middle and you get a 0 below and above it. Then you get a 1 in the lower corner here and you get zeros above that. And then your answers will pop out like that. So the pattern continues to 4 equations and 5 equations and 99 equations. But let's finish this one off. We did 3/4 times 0 is 0 plus 1 is 1. 3/4 times 1 is 3/4, and 3/4 plus -3/4 is 0. It's why we chose 3/4. And then finally, the last one's a little more difficult. It's 3/4 times 7, which is 3/4 times 7, and then I'm going to add this -1/4. So we'll have 21/4 minus 1/4 is 20 over 4, which is 5. We did it. Each row represents an equation. The first row means we have 1x plus 0y equals 5. And the second equation says we have 0y plus 1x equals 7. and, getting rid of the zeros there. Oh, sorry, I think I said it right. I wrote it wrong. 0x plus 1y equals 7 in the second equation. If we eliminate the terms that have a coefficient of 0, we're left with x equals 5 and y equals 7. And then we can check our answer. We already did check it. Remember, our equations were 4x minus 3y equals -1 and 6x minus 4y equals 2. We're just going to plug in our values for x and y and make sure that they work. So when x is 5, the first equation will be 4 times 5 minus 3 times 7, which is 20 minus 21, which equals -1, which is what it equaled. And check the other one just to be sure. 6 times 5 minus 4 times 7. So we get 30 minus 28, which is 2. So it works. You should never get one of these wrong if you have enough time, because you can always check your work. If these didn't work out, well, then go back and trace through and see if you made a mistake. I know what you're thinking right now. You're thinking, why are we doing this? We already know how a method for solving systems of equations, and it works quite well. Why are we learning this new one? Well, this technically isn't new. It's your, elimination method that you learned back, a million years ago. It's just different notation for it, really. It's a nice systematic, it's a nice algorithm that, will always get you there. Where the benefit of this method occurs is when you have larger systems. If you have 4 equations with 4 unknowns, this method will be a nice organized way of solving the system. If you try to use your old substitution method on 4 equations with 4 unknowns, you're very likely to make a mistake. I'm not saying you wouldn't make a mistake doing this either, because there are many, every time you rewrite it, you have the opportunity to make a mistake. But honestly, this is a very nice way to solve these. But you don't really realize it until you get to the larger cases, which take a long time to even show. So I think we can go back over to the PowerPoints and continue on from there. Maybe. So here's where we were. And the PowerPoint slides go through the same thing that we just did. It doesn't show much of the the little scribbles and such, but it gets you to the same place that we ended up in. But I wanted you to see it coming out of the pen. It's sometimes hard to understand what all these little labels are doing. Here are the rules we used. We multiplied a row by a constant. We added a multiple of one row to another row. And there's another rule that we can do. We could swap the equations around. Like there's nothing saying that equation 1 has to go in row 1 and equation 2 has to go in row 2. You can swap them and you'd still be solving for the same answer. So those are our basic rules still. And here's the 3 equations with 3 unknown case where you're trying to get your system to look like this. The pattern you use is you get the 1 in the upper left, and then you get the zeros below it. Then you get a 1 in the middle, and you get the 0 above and below it. And then finally you get a 1 in this row 3, column 3, and you get the zeros above it. If you do it in that order, you'll never go wrong. That isn't the only order to do these in. Sometimes it's more efficient actually to, kind of jump the gun and do it a little bit out of order. But it's hard to then write an algorithm that does it that way. I think if we learn one solid algorithm for this that always works, I think we'll have a good understanding of this. We're going to use this Gaussian or Gauss-Jordan elimination not only to solve systems of equations. This is also used in other places. The main place that we will use it will be to find the inverse of a matrix, which we'll see later. So, which again is important in computer graphics. So I know that you know other ways of solving systems of equations, but I want you to try to learn this Gauss-Jordan method because it is useful to other things as well. I just thought by starting with systems of equations, it's a topic that you already have a nice math background in. So yeah, the number of rows is the number of equations. The number of columns is the number of variables plus one to make room for the constants. And that's really the augmented part of the matrix, is including those constants from the equations. Here's another example. 3 equations, 3 unknowns. I thought maybe we could do this one old school too, even though I don't really want to. These things are tedious. You're going to have to practice quite a few of these before you're, proficient at it. It's easy to make mistakes, and it's hard to find the mistakes. The arithmetic, warn you, gets ugly in a hurry, even when you start out with fairly nice numbers. Here's a matrix that just has integers in it. There are no decimals or anything, and it still gets kind of ugly in its solution. But I'm willing to do it. So let's try that thing, by hand. We'll write down what the matrix was. So suppose we have a matrix. Whoa. Suppose we have a matrix that had the first equation as 10x plus 1y minus 5z equals 7. Remember, you have an x column, a y column, a z column, and then your constants. And then the next equation is 20x plus 3y plus 20z plus 4, or equals 4. And then the third equation is 5x plus 3y plus 5z equals 14. We want to solve these 3 equations using the Gauss-Jordan method. Sometimes they call this row-reduced echelon form. If you're Googling this, or why, if you decide you hate my video and prefer Khan Academy or something, there's row echelon form and row reduced echelon form to give you more things to Google than Gauss-Jordan, but they all mean the same thing. I'm not exactly sure why it's even named after Gauss, because I don't think he invented it. I think Jordan had more to do with this than Gauss. And Gauss is, more famous for basically inventing calculus. No, I digressed, but our goal is to turn this 10 into a 1. So let's do that. I'm going to leave the second 2 rows alone. So I'm just recopying them for now. And I'm going to change this 10 into a 1. To accomplish that, I just divide the whole row by 10. So it's basically, I'm going to take 1/10 times row 1. We said our rules were you could multiply a row by a constant. So I'm multiplying by 1 over 10. So I often write my little note here. So 1/10 times 10 gets me that 1. But I have to do it for every piece of it. So 1/10 times the y coefficient is 1/10. And 1/10 times the z coefficient is minus 5 over 10. And then 7 over 10. So we're 1/9 of the way done with this question. We have a 1 in the upper left corner. Our goal is to use that 1 to help us eliminate the values beneath it. So I'm going to do that in one matrix. I'm going to be leaving the first row alone. And I don't know why I didn't reduce 5 over 10 there, other than it might be easier to have them all in terms of tenths at this point. I'm not sure yet. My goal is to first wipe out this negative 20. To do that, I'm going to multiply row 1 by something and then add it to row 2. Well, what should I multiply row 1 by? The opposite of negative 20, which is positive 20. So in row 2 here, I'm going to have 20 times row 1 plus row 2. And that our answer will go here. While I'm thinking about this, I'm also going to wipe out this 5. And to wipe out the 5, instead of multiplying by 20, I would multiply row 1 by minus 5. So minus 5 times 1 plus 5. So row 3 is going to be minus 5 row 1s plus row 3. And that will go down here. I'm just saving having to rewrite the matrix one of the times. So I'm going to do 2 rows at once. You've done one of these before, and you're an expert now. Back to killing this negative 20 using positive 20. So 20 times 1 is 20, and 20 plus negative 20 is 0. I put my answer here. I look up here, put my answer down here. Now the next one's going to get a little uglier. So 20 times 1/10, well, that's not too bad. That's 2. And 2 plus 3 gets me 5. Continuing on. Now multiply 20 times negative 5/10. Well, that's negative 10. 20 times negative 5/10 is negative 10, and negative 10 plus 20 is 10. If that hurts your brain, scribble it out on the side. 20 times negative 5 over 10 plus 20. Do your cancellation here. You get negative 10 plus 20 is 10. And then we'll do the same thing. The last one here, we have 20 times 7 over 10 plus 4. So that's 14 plus 4, which is 18. Whew. We got our 0 here. Now I want to get a 0 here. And to do that, instead of multiplying row 1 by 20, I'm going to instead multiply it by negative 5. I'll just cross that out maybe and write negative 5 here. Negative 5 times 1 is negative 5 plus 5 is 0. Then we have to do it for the rest. Negative 5 times 1/10 is negative 5/10. Negative 5/10 plus 30/10 is 25/10. If you're not sure, negative 5 times 1/10 plus 3, which is negative 5/10 plus 30/10, which is 25 over 10. Maybe it would be better to reduce it. I'm not sure. That's 5 over 2. The next one, negative 5 times negative 5/10 is 25 over 10. Then we have to add that to 5. So we'll have positive 25 over 10 plus 50 over 10, which is 75 over 10, which is, well, maybe I'll just leave it like that, 75/10. You guys have your calculators too that can help you out as you go along here if this is freaking you out. If you reduce that, I guess, what is it, 21 over 5? Or, sorry, over 2. So it might be nice to have these in halves rather than tenths. I'm not sure. And then finally, negative 5 times 7/10. And then add that to this 14. Our answer goes here. So you get negative 35/10 plus 140/10. See, I like the tenths. Easy to find common denominators. So we get 105 over 10. And that's where I had the 21 in my head from. You guys should be yelling at me right now. If we're doing this live, you'd be yelling at me. 75 over 10 is not 21. When you divide it by 2, or divide it by 5, it's 15. And this one, if I divide by 5s, I get 21 over 2. Still aren't the nicest numbers, so I'm just going to leave it as 105 over 10. We're getting there. Our next step will be to turn this 5 into a 1 and then use the 1 to wipe out the value that's above it and the value that's below it. So I'm going to leave the first row alone for this step. And I'm going to leave the last row alone. And I'm just going to work on turning this 5 into a 1 to make 1s just multiply by their reciprocal. So I'm going to take 1/5 times row 2 and put my answer right here. My new row 2 is 1/5 of old row 2. Sometimes we write it that way. R2 new is 1/5 R2 old. And old meaning the previous matrix. So I just like to write a little cheat up here. 1/5 times 0 is still 0. So it didn't mess that 0 up. 1/5 times 5 is 1. 1/5 times 10 is 2. And 1/5 times 18 is 18 over 5. Might be better if I write it as 180 over 10, so I have everything in terms of tenths. But I'll leave it for now and see what happens. The next step of this process is we want to wipe out this 1/10 and we want to wipe out this 25/10. We'll do it in 2 separate steps. I'm just going to do it in one matrix though. I'm leaving row 2 alone. I have to ask, what do I multiply by row 2 such that when I add it to row 1, I eliminate 1/10? And the answer is going to be negative 1/10. So negative 1/10 times row 2 will be added to row 1 and be placed here. Negative 1/10 of row 2 old plus row 1 old equals row 1 new. We'll do something similar when we want to get rid of this 25/10. We'll say negative 25/10 row 2 plus row 3. We'll go into this new row 3. Away we go. I'll just write my little note. I write the note next to the row that I'm working with here. So I'm going to take negative 1/10 and multiply it by this middle row and add it to the first row. Negative 1/10 times 0 is 0, and 0 plus 1 is still 1. Negative 1/10 times 1 is negative 1/10, and negative 1/10 plus 1/10 is 0. Negative 1/10 times 2 is negative 2/10, and negative 2/10 plus negative 5/10 is negative 7/10. And then negative 1/10 times 18/5 plus 7/10 is getting to be too hard, so I go and scribble it off on the side. Negative 1/10 times 18/5 plus 7/10. It didn't really reduce, I can't cancel too much there. Probably just as easy to write it as, that's negative 18/50 plus 35/50, which is 17/50. And that's what goes in this spot. You see the fractions get kind of ugly. I can come up with examples where the fractions don't get as ugly, but I thought that's kind of unfair because most of them end up more like this than ending up with all nice integers the whole way through. So I thought it was best to do an ugly example so that you could see that that's how they typically are kind of ugly. Well, we're getting there. We got a 0 where we wanted it. Our goal next is to get a 0 right here, below the 1. So to accomplish that, we said we're going to, maybe I'll just leave that there, cross it out. I'm now going to multiply row 2 by negative 25/10. Why? Let's see. Negative 25/10 times 0 is 0. And 0 plus 0 is still 0. It didn't mess it up. Negative 25/10 times 1 is negative 25/10. Add that to positive 25/10 and you achieve your 0 here, which is what our goal was. Now the next two spots will be a little bit ugly. Negative 25/10 times 2 plus 75/10. So negative 25/10 times 2 plus 75/10, which ends up being just 25/10. I can't get it to right. Or 2.5, since it's exact. This spot here is now 25/10. And now we have one more spot to go here. Negative 25/10 times 18/5. And then we're adding that to 105/10. Here it might be worth it to do a little cancellation. This 5 goes into 25 5 times. So we're left with 18 times 5 here, which is 90. So we get negative 90/10 plus 105/10, which is then 15/10. or 1.5, since it's exact. We could be using decimals in here, especially when they're exact. I just prefer to stick with fractions. That way you never have to worry about any sort of rounding. Because if you round, then suddenly everything from that point on, you'll be making a mistake. We're 3 or 6/9 of the way done. We need to get a 1 in this position. I will leave the first 2 rows alone. Hopefully I won't make a mistake when I recopy them. It's the worst thing in the world when you're doing these. If you make a mistake, it's so hard to find it. I want to get a 1 here so that I can then use the 1 here to get zeros above it. So I'm basically creating that pivot. What do I multiply 25 over 10 by so that I end up with 1? Well, 10 over 25. 10 over 25 times R3 old gives me R3 new. I'll just write it up here. 10 over 25 times 0 is still 0. 10 over 25 times 0 is still 0. 10 over 25 times 25 over 10 is 1. And then finally, 10 over 25 times 15 over 10 ends up being 15 over 25. The 10s cancel. I could probably reduce that. In fact, I think I'm going to. Divide by 5, so we get 3/5. We did 10 over 25 times 15 over 10. I canceled these 10s and ended up with 15 over 25, and then I reduced. Divide by 5, you get 3/5. Next, we want to get zeros here and here without messing up any of the stuff that we've already done. To accomplish that, I'm going to rewrite the last row because it's done. I know my last variable z equals 3/5. 0x plus 0y plus 1z equals 3/5. So z is 3/5. What do I multiply row number 3 by so that I can eliminate the 2? -2. -2 row 3's plus row 2. And I'm also going to eliminate the -7/10. So I'm going to multiply by +7/10. So 7/10 times row 3 and add it to row 1. And I'll put the answer up here. We'll do those 2 steps. I'll do row 2 first. So I'm going to do the -2 first. -2 times 0 is 0, and 0 plus 0 is still 0. -2 times 0 is 0, and 0 plus 1 is still 1. -2 times 1 is -2, and -2 plus +2 was strategically chosen so that we get a 0 here. And then the last one's the hard one, -2 times 3/5, and then add 18/5. So we get -6 over 5 plus 18 over 5, which is 12/5. We're almost there. Finally, let's eliminate this -7/10 in row number 1. To eliminate that value, we're going to multiply row 3 by +7/10. 7/10 times 0 is 0, and 0 plus 1 is 1. 7/10 times 0 is 0, and 0 plus 0 is 0. I bet this is really fast on 4x times 7 tenths times 1 is 7 tenths, and 7 tenths plus negative 7 tenths is 0. And then finally, 7 tenths times 3 fifths plus 17 over 50. So 7 tenths times 3 fifths plus 17 over 50. That's actually not too bad. What do we have? 21 plus 17 over 50. That's 38 fiftieths. I guess that reduces 19 over 25. So for this system of equations, the first row tells me that x is 19 over 25. The second row tells me that y is 12 over 5. And the third row tells me that z equals 3 fifths. That's the solution to our system. Not too bad, I hope. We should check our answer as much as we probably don't want to. We need to substitute this back into our original equations, which we probably don't even remember because they're so far back here. And I didn't even write them all out. Here, I'll grab this. Maybe I won't do that. I don't know if it grabbed all the numbers in between. It looks like it. Okay, so here's where we started. Remember what this translates to. You know, the first equation there is 10x plus y minus 5z equals 7. And the next equation was minus 20x plus 3y plus 20z equals 4. And then the last equation is 5x plus 3y plus 15z equals 14. You could go ahead and solve this using substitution or, a regular elimination and to check it as well, I suppose. But it'd probably be easier for us now to just do the substitutions here. So let's plug these values into these three equations. The first equation will be 10 times 19 over 25 plus 12 over 5 minus 5 times 3 over 5. And let's see if we get 7. I guess I could reduce a little bit here. Divide both by 5 here. So I get 38 fifths plus 12 fifths minus 15 fifths. What is that? 35 over 5, which is 7, which is what we're checking. So it worked in the first equation. I feel pretty good about it. I probably could risk it and not check the rest, but you really should check the rest just in case. It's possible to come up with an answer that works in one of them but didn't work in the other two. So just for completeness, let's do this. Negative 20 times 19 over 25 plus 3 times 12 over 5 plus 20 times 3 over 5. A lot of arithmetic today. Maybe I'll reduce this fraction 2 down to fifths. So what do we have here? Negative 4 times 19 is negative 76. Plus 36 over 5 and plus 80 over 5. 60 over 5. Oh boy, that would have been bad. So negative 16 plus 36 is 20 over 5, which is 4, and it matches. So we're 2 for 2. Just to be 100% sure, we'll do the last one too, I guess. X was 19 over 25, Y was 12 over 5, and Z was 3/5. Again, getting this back to fifths. It's gone. So we have 19/5 plus 36/5 plus, oh geez, it's hard. Let's just do it. So we had 19/5 plus 36/5 plus 45 over 5. Leaving us with 70, 81, 90, 100 over 5. No, that can't be right. 19 plus 36 plus 45 is 100. That equals 20, and that isn't 14. Oh no. Oh no. Where did we go wrong? Did I get my coefficients all right when I copied this over here? Oh, I goofed it up right here. Oh, thank goodness. When I wrote my equation, I wrote 15z instead of 5z. So what changes here? This should be a 5, which means this should be a 5, which means, well, this should be a 5. Or that should be 15 then. I should really practice these ahead of time. But now I think it's going to work out. Because now we have 36 of 46, 51, 60, 70 over 5. And 70 divided by 5 is 14. Whew. I was worried. It checked out. So that was a lot of work. I hate to get to this point and blow it at the very last step. But it happens. So moral of this story is practice a bunch of these, even though they are painful to do. We can zip back over to the PowerPoint, and it traces through it too. We can just trace through. It does it. I do it a little quicker just to save space on the PowerPoint slide. I let it go into decimals because they were all exact values anyway. And you'll see I was able to accomplish this with maybe a few less rewrites than we did when we did it by hand. But just so you can see the process is the same that we did. Basically, when you're doing this, you work column by column. You start in that upper left corner to get a 1 in that first pivot position. You use that to kill the numbers or eliminate the numbers that are beneath it, or you eliminate any other values in that column besides the pivot. What are you allowed to do? Multiply a pivot row by a constant and then combine it with another one. You can also swap rows around if that makes things easier, which sometimes is the case. You can actually switch columns around while you're doing it, but you have to be very careful when you do that to make sure that you remember that when you switch the columns around, you know what each column still represents. So I don't really recommend that actually, but it can be done. Yeah, and we can multiply multiples of pivot rows times other rows. So I was just trying to write out the steps that we did here, and you just keep repeating basically that technique over and over. Get a pivot, then use the pivots to eliminate the other stuff. Get another pivot, use that to eliminate the other values in that same column. Continuing on, continuing on. If you have a 100 by 100 matrix, 100 equations with 100 unknowns, you're going to do this. This is going to take you a while, but you can see that it's one algorithm that, it's easy to automate this. So it's not too hard to get a computer to actually do Gauss-Jordan elimination, with a couple of for loops. I think that's where we'll call it for today. We'll continue on with this in the next video. We'll do another example of Gauss-Jordan, of course. We'll talk about the cases where sometimes there isn't a solution, or sometimes there's more than one solution. And then we'll move on to other things like matrix operations. So I hope to see you there. Take care for now, and I'll see you next time.